right? So as you know that this is the structure of the microstrip antenna, as you can see here. And then for this one, it shows you in terms of the different element. What we can hear is element length versus frequency for different dielectric substrates. Okay, from this, what can you see for the microstrip antenna here? Is there anybody can give me a response? From this graph, what can you say about the microstrip antenna here? To switch on another one, otherwise I can't listen. I can see yours. From the graph given here, element length versus frequency for different. This graph, okay, if we, let's say we take about this frequency, for example, okay, can you see this? This is at maybe 2 gigahertz, for example. No, not really 2 gigahertz. Yeah, maybe 2 times 10 to the power of, let's say 2 gigahertz here. What can you say about this? If you increase, if you talk about the substrate here, if you increase the value of the substrate, so as usual, you can see that the length will be reduced, right? Because it means that it shows that if you want to make your antenna smaller, what you need to do, you need to increase the substrate of your antenna itself, right? So this is one of the important thing. So if you want to make your antenna more compact, for example, you can increase the substrate of your antenna. So from this graph, and as well as in terms of thickness, it's not really, it's not really, right? In terms of the thickness, almost you can see that the thickness is almost the only thing that the thickness happen when it goes to very high frequency here. Okay, so this is the most important thing in the length of your antenna. Here, as you can see from this particular graph, if you want to make your antenna smaller, one of the methods that you can use is by increasing the epsilon r. So once you increase the epsilon r, your length will be reduced. Because how? Because as you can see that the guided wavelength here actually is equal to lambda naught over epsilon r. So usually we look in terms of your lambda g. It's happened in your microstrip antenna. Okay, right. So this is the most important thing in. So I mean that you know already, if you want to increase or if you want to make your antenna smaller, one of the method you can increase the substrate of your materials. In this case, as you can see that here, if you increase the substrate, you can find out that your L here is getting smaller and your antenna can be compact. So this is one of it. But you know that if you increase the substrate of your material and then you increase the thickness, what happened here is you are producing more surface wave. Surface wave is happening if you have in terms of the thick substrate. Okay, so we look later about that. Right, so next as I mentioned to you before, the design procedure here is include that, of course, you need to know, usually what you have, you know the substrate, you know the substrate value, so that means you can find it from the manufacturers, but usually if you want to have like a very simple structure, substrate, what we can do, we can use a cheaper one. And so that's why usually sometimes most of my students, if they are doing on the low frequency, we are looking in terms of the FR4 only. Because why? FR4 is very cheap and the epsilon R is roughly about 4.4 to 4.7. The problem for the FR4 is in terms of this particular dielectric substrate here. Because the dielectric substrate is not constant. It's not constant. So that's why the substrate of R4, sometimes if you design, you can have some different values from your simulation because of the epsilon R is not the same. And another one is the tangent. The tangent loss, the delta is very high, 0. If I'm not mistaken, is 0.019. It's nearly about 0.019 or 0. I think 0.019 or roughly about 0.02. So if you have a very high tangent delta, so what you can see that the value of losses also will be very high as well. Okay, so that's why for high frequency, you are not suitable to use a FR4 anymore. Maybe up to 4 or 5 gigahertz is okay, but above than that, as you can see, that it's not really suitable. It's not really suitable, especially for the millimeter wave. So that's why for the millimeter wave, you can see that you have a very, very expensive substrate, a microwave board, so that you can have a better in terms of the results. Okay, so usually what you need to do, you specify what is your epsilon R, you specify what is the resonant frequency that you are going to use. For example, if you are going to design at 3.5 gigahertz, for example, 3.5 gigahertz here is using for the 5G application. Okay, anybody knows what is the length of this? Okay, so can you calculate what is the value of with, for example, with your epsilon R is equal to 4.4. Okay, I want you to find out what is the W. Okay, so you want to determine W and L. Okay, at this particular 3.5 gigahertz. Okay, I want you to find W and L here. So how you want to find W? W can be found from this particular equations here. As you can see, V naught here actually is equal to 3 times 10 to the power of 8 meter per second. And then the one is L is equal to this. Let's say if you are not talking consideration, so this delta L is the fringing field. Let's say you say that fringing field is not taken into consideration. Can you find out what is the W and L at 3.5 gigahertz here? Okay, can you calculate it for me, please? Okay, now I want you to calculate what is the W and L in this particular design. If you want to design at 3.5 gigahertz with your epsilon R is equal to 4.4 here. Of course, you need to find what is the epsilon effective here. Okay, in order for you to get the L here. Chai Chu Kian, can you give me what is the W here? What is W? Very easy, simple equations given here. So the W actually is equal to 3 times 10 to the power of 8 over resonant frequency is 3.5 gigahertz, square root of your 2 over 4.4 plus 1. So what is this W? Chai Chu Kian, can you get the answer? 26 millimeter. Okay, 0.026. So it means that equal to 26 millimeter, right? Okay, so what is your L now? I want you to find L, Lee Chunxian. What is the L here? You can use this equation, L, with just epsilon R effective. You assume as there is no fringing field here. I assume as there is no fringing field. So the most important thing here, you need to find what is the epsilon effective here. How is it the epsilon effective? You can use these equations that are given to you before. Okay, so epsilon effective is this one. This equation is the epsilon effective here. Okay, you can see that epsilon R effective. So H, you know, let's say if we assume H is equal to 0. Let's say I thought 1.6 millimeter. In this case, I assume that my H is 1.6 millimeter. W, the values that you are getting from 0.026 here before, and then you put into this equation epsilon R effective. Epsilon R, you know, is a 4.4.
Yeah.
Okay, when you add all this, what is the epsilon effective here? Okay, I want you to give the answer.
Okay,
I'm not going to give you the answer. Okay. Lee Junzian, can
Yes.
you calculate and
Can
give
you
me
show
the
me the
answer?
show me the formula again?
What is epsilon R effective?
Doctor, can you show me the formula again for the just now?
I have the notes. You have the notes, right?
Yeah.
I give.
Hello, sir. Dengar?
Yeah.
Ah,
Dengar.
okay. Z0 kita apa?
Z0 kamu kata assume as 50 ohm. Usually as RF, we assume as a 50 ohm.
50, okay.
Dalam ni tak ada pun Z0. The values that you need to find is epsilon effective, isn't it? Is equal to what? Epsilon R plus 1 over 2 plus epsilon R minus 1 over 2. Okay, 1 plus 12 over W negative 1 over 2 here. Okay, so this is the only thing that you need to find. Epsilon R, you know, H, you know, I say that H is 1.6 millimeter. And then I say that W is, you got, okay, everybody got, they say that you got 26 millimeter as well. So you can just put W is equal to 26 millimeter. So from here, you calculate what is your epsilon R effective. Okay, so
Doctor,
epsilon
I got
R
2.8.
2.8.
8.
0.8 or so, is it? Okay, I want the other answer.
3.99.
Yeah, I think
3.99.
that's more correct. Okay, 3.99 or nearly 4. Okay, as you can see that here, you see, epsilon R effective usually should be less than your epsilon R. Because, why? Because as you can see that, okay, so this is your substrate, epsilon R, and you have the air here, epsilon R is to 1. So the combination of these two, you have to find in terms of the epsilon effective. So the value must be less than 4.4. Okay, so, and then, all right, so Mustafa, I want you to find out what is your L now without your fringing field here. L is equal to 3 times 10 to the power of 8 over 2 resonant 3.5 times 10 to the power of 9. Epsilon R, let's say you got 4 here. What is this value? So if I say that there is no fringing field here, so there is no delta L is equal to 0 here. You know that your W here.
It's about 0.021.
21 millimeter.
21
Is
millimeter.
it?
Yes.
Okay, how about the rest? Do you get the same answer?
I get 0.015 meter.
0.015 meter is too small. I don't think so. The rest, Ang Zong Yang, what is the answer that you get for L?
0.02 meter.
Okay, so roughly about 20 millimeter or 21 millimeter is okay. So as you can see that if you design your antenna now, okay, so the most important thing now you can see that your L is 21 millimeter and your W is 26 millimeter here. Okay, so this is the answer that you will get in this particular values if you obtain this particular value. Okay, so you know already how to design your your very simple patch antenna here. Okay, right. So the next I want to show you how you want to fit because usually if you have this kind of patch here, as you can see that you need to match it with your transmission line. Okay, so you need to match it with your transmission line. Match your transmission line here. So as I mentioned to you before, in terms of the matching, we also have in terms of a different techniques where you can match with your impedance, as you can refer from my notes before. So we can match your antenna with the transmission line. We can match using the coaxial line. We can match into proximity, aperture couple, or sometimes with the coplanar waveguide. So this is a technique that you are going to match with. One of the techniques, as you can see here, is the inset feed position, where you need to find here, let's say, for example, this is your W. So this is your fringing field, for example. So now you want to match your antenna toward this fringing field with your transmission line. So you want to find the position here. Where is the positions that it can match with 50 ohms? Once you have this, so you put some sort like your inset feed here. So you can match. So at this point, we know that this is a 50 ohm. So if you have this 50 ohm, so you need to find, or you need to design the transmission line with a 50 ohm as well. Okay, you need to find the transmission line with a 50 ohm as well. Okay, so what you can see that you want to find what is the position here. So this is the values that you need to find here. I put it there here. The value is roughly about why not here? Why not the position where the inset feed here is roughly 50 ohm. So the most important thing for the microstrip is your W naught. So that means you need to design the microstrip with the W naught of your 50 ohms. Right. So this is normalized. This is the graph to show that in terms of R in Y equal to Y naught and R in Y is equal to 0. So this is at the edge here. As you can see, this is at the center here, 0.5. So this one is a Y naught over L. So you can see this is the graph shows in terms of this impedance towards your length. So as you can see there at the center here, so usually the value is very low compared to at the edge here. This one you can see that high impedance or high resistance, and at here is a low resistance. So at the center here, as you can see that this is a very low resistance. So it means that maybe it nearly can become 0 here. So that's why you can see that here you have a minimum values of your impedance. So it means that you have here is a high value, high, and when you move here it becomes 0. So that's why you get this kind of graph towards this positions. So it means that if you want to find here, so what is this? Okay, so you can get it from this particular graph as well, or you can do some calculations from here. Okay, so if you're using the model expansion analysis, it has been shown that the inset feed point impedance is given by R in, when R in is to Y to or not, and R in is Y to the, Y is to 0 is where this is at the RH. Sometimes I put the RH here. Cos square pi over L multiplied by Y naught. Y naught is where is the positions that you want to find. L is the length of the patch. As the inset feed point distance Y naught increases, the resonant input resistance decreases. In fact, at Y naught is equal to L, the input resistance vanishes, so it becomes 0. This feeding mechanism can be very useful for matching patches to line with the small values of calcium impedance on the order of 50 ohm. Okay. Okay, so this is example. You can see that for G1 is less than Y conductor here, and B1 is less than Y. So this is at the R in here, as you can see that this is between conductance and the mutual coupling here. We consider this as well. So this is at the RH here. Okay, so if you have like this, W and L, So at this particular point, this is the RH here. Okay, so in this case, they consider in terms of the mutual coupling between these two slots when we model it before. Okay, so and then you need to find out what is the Rin if you have the 2G1 plus 1 minus G12 here for odd voltage or for even voltage. As the values of Y0 approaches L/2, the cost function varies rapidly. Therefore, as the feeding point approaches the center of the patch, the input resistance changes rapidly with the position of the feeding point. So in order to maintain very accurate values, a closed tolerance must be maintained. And to illustrate that, let's consider an example here. So what we can see that the relation is R in Y to I naught equal to this. Predict the resonant resistance value will and the values agrees reasonably with the experiment. However, because of the physical notch into by the inside feed here, the resonant frequency may vary about 1% due to the capacitance introduced by the junction here. Okay, so what we can see that since the resonant input resistance is equal to this one, we consider only 2G1 here, so we can do in terms of this particular value. Zeta naught here is equal to 37, lambda naught is your frequency, W is the width patch. Okay, for example, if you take consider that is equal to 1 over 2G, G1 is represented by this particular equation. The resistance can be decreased by increasing the width of the patch. This is usually acceptable as long as the length of the patch is maintained to about half over 2. Usually ratio of 1 W over L greater 2 are not recommended because the aperture efficiency of a single patch begin to drop. This can be avoided by using multiple feeds. Okay, so that's why you just want to find out your W usually is greater than WL because of you want to have a better in terms of the effect aperture or in terms of the gain of this particular antenna. Okay, so this one I show you what is the effect in terms of the feed location. So this is just an example of how the feed locations varies. Okay, varies in terms of the position. Okay, so this input impedance B is VSWR, and then C is the radiation patterns here. Okay, E plane, copolar, and cross polar, H plane, copolar for infinite ground plane. With the increase in X, the input impedance plot shift right towards higher impedance value. Okay, if you have effect of width here, okay, so what happened towards your VSWR plot of rectangular microwave antenna for different W. Okay, so this one is just show you in terms of this effect of thickness, H of your substrate. What happened, as you can see that the bandwidth is proportionate to H over lambda naught. However, H over lambda naught should be less than 0.3 over 2. So these are some of the parameters that maybe you can look in terms of this patch antenna when you are going to do the second assignment later on. So this is a parameter that you can get it from the software from your simulations. Okay, this one is the effect of the probe of diameter. Okay, what happened as a probe diameter is in the inductance increases, so resonant frequency decreases, and input impedance locus move forward upward to the inductive region. And then effect of the loss tangent, as you can see that loss tangent is your tangent delta here. With increase in the tangent delta, the dielectric losses increase. So input impedance locus move left towards lower impedance value. Bandwidth increases by efficiency and gain decreases. Okay, so this one is effect of dielectric constant epsilon R. Okay, as you can see that when your epsilon R is increases, you can see that increases here. So the L will become very lower. Of course, W also getting lower. and the position X here is also F naught. This is the resonant frequency that you have. R in here, bandwidth, and the gain. As you can see that the most important thing here, you see, if you increase the epsilon R, your gain also will be reduced. So that's why we are not really using the higher epsilon R. The only thing that they use the higher epsilon R because they want to reduce the size of the patch so that it can be suitable mounted in your whatever devices that you want. With decrease in epsilon R, both L and W increases, which increases the fringing fields and aperture, hence both bandwidth and gains are increased. So that's why you see, if you increase here, you increase or you reduce your epsilon R, the bandwidth and the gain will be increased. So this is why you need to have a certain epsilon R in order for you to have to compensate between the bandwidth as well as the gain. Okay, if you use epsilon R is very high, you see the bandwidth also is very small compared to the lower epsilon R. Okay, so this one is effect of finite ground plane here. Okay, so and then this is the radiation pattern for the microstrip in terms of E plane and in terms of the H plane here. Okay, so we define E plane when you take consideration of your theta is equal to 90 and you have a 0 less than 90 and you have a phi here is between 270 to 360 here. For the H plane, we know that phi is equal to 0 and theta is 180. So you can put into this equation, you can find the value. Okay, let's say for example here, okay, so in this example, you need to find out what is the W by having all these value. Okay, for example, you are given a duroid with epsilon R of 2.22 and then you have a thickness. We take consideration in terms of the metric system because in US sometimes they are still using the feet and inch. Okay, so and then the resonant frequency is 10 gigahertz. So this is the RT duroid 5880. So this is a specification for the substrate. So spec substrate, we have epsilon R is equal to 2.2 and the H here is 0.15 centimeter. Okay, so if you have these two values, basically you can find already the L and W. First of all, what you need to do, you need to find the W. Okay, so from this equation, when you put all this equation, you can find that W is 1.186 centimeter. Okay, so if you don't agree, you can recalculate by yourself and see whether you are getting the same answer or not given. And then if you want to find L, what you need to do, L is actually half wavelength over 2, you minus with 2 delta L. So of course, half wavelength here, you have the epsilon effective here. Okay, so epsilon R effective here. Actually, it's epsilon R plus 1 over 2 plus epsilon R minus 1 over 2, 1 plus 2H over W. Okay, so when you calculate this value, you can see that you will get 1.9726. You see, this epsilon R is slightly lower than the epsilon R given from the substrate. Okay, so everybody should know that. And then you got the value of SRI 1.9726. And then you need to find out what is your, because you want to find what is the fringing field here. Okay, so as you can see that this is your L here. This is your W. So this is your fringing field here. The fringing field come from this L here. So this is your delta L. So this is your delta L. So you have 2 delta L. So you have to be minus with your delta L. So this is the effective of your length of your antenna due to this fringing field as well. You calculate in terms of the fringing field. The fringing field value usually is very, very small. Okay, now you want to find what is your delta L here. If you calculate your delta L, so you got your delta L here is actually is equal to 0.018 centimeter here. Okay, so I'm not looking into of the inch because we are not from the US, because we are using the British system. So in the metric, so you got delta L is, and then if you want to find what is your L effective here, so del lambda over 2. Lambda you need to find out is into of lambda G here. Lambda G is to lambda naught over 2 epsilon effective. So lambda naught here is actually is equal to C over F. So you know that lambda G here, what is it? This is lambda G. Lambda G. So lambda G is equal to lambda naught over 2 epsilon effective. Okay. So lambda naught over 2 epsilon effective C over F. So that's why you got C over 2 multiplied by F. Okay, so you can see that it's almost similar with the previous one that I'm show to you lah. Okay, C over 2F multiplied by epsilon effective. Okay, so once you have this value, okay, so when you calculate this value and then you take consideration into L effective because you're just taking L plus 2 delta F. Okay, basically your L here actually is equal to L effective. You minus with 2 delta F with the L. But in this case, you consider that some fringing field here. So you add and then you got equal to 1.068 centimeter here. Okay, so what you have, your W is 1.186. 1.186. This one is 1.068 centimeter. Okay, so this is the patch that will be operating at 10 gigahertz. Okay, so operating at 10 gigahertz here. Okay, so you know already your L and you know already what is the W. So once you design this patch antenna, we know that the antenna will be operating at 10 gigahertz. You can imagine that you see the size, the patches is very, very small. Okay. All right, just a very quick exercise here, just very quick. Can you find it for me? What is the W and L if you are using at 28 gigahertz using the same values of your substrate and thickness in this example? Okay, just try to do it by yourself. Okay, so for example, this is the example of the microstring antenna. Okay, what is the value of W and L if the operating frequency is changed to 28 gigahertz. The same substrate and thickness is being used. Just find for me what is the W and L. Okay, everybody, I want to ask you later on what is the answer that you're getting. First of all, your design, you should design, you find the W first. Exam test ada. Classes no. Where he has been? Siapa tahu? Is there anybody, Nor Irda? You want to say something? What is the W and L here?
W 4.24 millimeter.
W is equal to 4.24 millimeter. Very small. L, Tashrik, what is the L?
Saya dapat 3.61 millimeter.
Okay, so you can see it's very small. 4.24 millimeter. You can imagine the size of the patch. It's only this particular size. Okay, the rest, everybody got the same answer or not? Just let me know. Okay, so this is how you can get W and L. Simple patch antenna, how you can design it. All right, okay. So next I want to show you in terms of the E-plane. Because everybody, please let me know if you are getting the different answer. Okay, if you are getting different answer, please let me know so that I think we can check with others as well. Aiman dapat apa? Sama tak ataupun tak buat langsung? Wah, Aiman Syafiq. Aiman?
Ya, Prof.
Dapat tak jawapan dia?
Kejap tengah baru dapat apa tu? Epsilon efektif.
Oh. W?
W 4.235 mm.
Okay lah, okay. Ainin Sophia, do you get the L? Okay, so this is the E-plane and this is the measured, you see, you do the measured and then they calculate in terms of the moment. Okay. Okay, so this is the E-plane for the microstrip and this is the H-plane for the microstrip antenna that you obtained before. The one before, this is at the 10 gigahertz. And if you want to find the directivity, as I mentioned to you so many times, U max over U naught 4 pi U max over P radian. So asymptotically, you can see that the directivity for the microstrip patch antenna is given as this particular value. So the value is 6.6. If you talk about W is less than lambda naught. Okay, from the previous, what is your W? W is equal to, what is our W? Is 1.186. 86, okay, at 10 gigahertz. Yeah, we're talking about 10 gigahertz. And what is the lambda naught? It is C over F here. C 3 times 10 to the power of 8 over F is 10. So what is this value? Anybody can give me the answer? What is this value? I don't have the calculator to calculate it for you. Okay, what is this value, please?
0.03.
Sophia? Apa dia, Aiman?
0.03.
0.03, 0.03, it means that 0.03, so roughly about 3 centimeter. So 3 centimeter, it means that the W is greater than lambda naught, isn't it? Or W is less than lambda naught. If your W is 1.186 at 10 gigahertz and lambda naught is 3 centimeter, so W is greater than lambda naught. Is it correct or not? I need Sophia. I want to listen this voice. I think he's missing. She's missing somewhere else. I need Sophia. Can you answer me? Ataupun duduk atas katil dia tidur kot. So W is less than lambda naught. So if your W is less than lambda naught, so you have to use this directivity. So the directivity is actually 6.6. So it's roughly about 8.2 dB here. So once you do the simulation, sometimes you know that you are getting this value should be less because of why? Because of you have some tangent losses of your dielectrics. So that's why you are getting less. So that's why your G here is to efficiency multiplied by D. Efficiency will determine the gain of your antenna. Okay, so this is some of the directivity given in terms of the graph and directivity, okay, versus your substrate line. And we also have the beamwidth. Beamwidth can be written as this particular example here. You see? So you have the E-plane. So the beamwidth, it actually is your angle. For example, you want to find what is the beamwidth here. So usually the beamwidth is actually is a 3 dB value. Okay, so you have your theta here. So this is for the E-plane and this is for your H-plane. So if you want to calculate your E-plane for the beamwidth, you can use this. And if you want to find what is the H-plane for the beamwidth, you can find it. This one L is the dimensions of your patch. H is what? Your substrate thickness. Lambda naught is your frequency. Pi is your pi value lah. And then this one is the wave number. K naught here actually is a 2 pi over lambda naught. And this is the W. W is the width. So if you know all these values, so you can find the theta E and theta. Okay, from the previous examples that I gave it to you, what is the theta E and theta W here? Theta E and theta H here, beamwidth. Okay, so what is your theta E here? And theta H here. Okay, from the patch that we obtained before at 10 gigahertz here. So L is 0.06, W is 1.186, 1.186. L is 0.906. Epsilon R is 2.2. H is 0. H is equal to what? Given 0.1558. What is this answer? And then you put into this equation, W is given as 1.186 centimeter. Make sure that you change to meter all. Okay, once you put this, so you are cost, and then you got this value. What is the value?
Untuk data E, kan?
Theta E, theta H, theta H. I'm talking about theta H is a bit more easier to calculate. Theta
Kejap.
H.
Data H belum ke? Data E je pun.
Theta E kau dah apa?
3.14 betul lah.
3.14 apa?
Unit dia tak
Degree.
situ. Degree.
Pi radian. Takkan 1.0 I think the answer that all of you given is a bit wrong. Okay, never mind. Tarik theta H. Kalau tengok dekat sini pun tak ada lah sampai tu. Roughly about 80. Suppose lah you get. How come that everybody is getting 180? Kalau kamu tengok saya lukis tadi lah. Kejap kalau sini lebih kurang lah. Mungkin ni 15, 10. Katakan saya ambil 10 di sini. So roughly about 80 This one also same lah. Roughly 80, 90 It can go up to 90 degrees. Okay, kalau yang kamu punya calculate. Okay, just to confirm your theta H. What is the theta H now? Norirda dapat tak? Norirda. Norirda.
Salah apa Prof? Dapat nilai lain. Pelik.
Pelik sebab apa jadi macam tu?
Sebab saya salah tengah kalkulator kot.
What is the values that you're getting here? Theta H, 2, cos. What is this value? What is the value in this bracket here? 1/2.
123.64 degree. I mean under theta H.
Theta 1, 2, 3 Still bigger. Because from the diagram itself, as you can see, is it from here, the 3 dB value is here only. The highest may be 90 lah, what we can say 90. If it means that if you have like this, 60, 120, you mean that your half is here. So this is not a 3 dB already. It's more than that already. 3 dB must be somewhere around here. Okay, right. So never mind. It's okay. So you try to do it at home. Try to find out what is the values that you are getting here. Okay, so as a conclusion for microstrip here, you can put here the microstrip. So of course, parameter. Okay, dimension here. So L, W, you can find the what? Directivity, theta E, theta H. Okay, so you can find all this value for your microstrip antenna. Okay, where is this? So now we want to see the positions. The position also is important in the microstrip. Okay, so what you can see that you can find the positions, the points that you want to match here. So this is your L here. This is your W here. So you want to find where is the position that is matched. 50 ohms here. So you can use this particular equations to find where is the position that you want to get your antenna. This is for R in is to R not. Okay, so you have to use these relationships here. Okay, so the positions of your R in here. So R in Y is to I naught is equal to R in Y is equal to 0 multiplied by cos pi over L Y naught. So R in here, actually what you can do, you can use 1 over 2 zeta is zeta naught lambda naught over pi W. So this one you want to find at the edge here, and cos pi Y naught over L. So you want to find what is your Y naught here. So the positions of this to show that this is at the matching point, so that you can match with your 50 ohms here. Okay, so this is very important to know this. Okay, right. So the next I want to show you is in terms of the microstrip square secular. Actually the secular microstrip is, you know, that the patch is in the secular form lah, like this. So you see, so the most important thing for the secular, for the rectangular, we want to find what is your L and W here. For the secular, you need to find the A here. So the radius of your patch itself. The radius of the patch will determine the operating frequency of your secular microstrip. Okay, so this is an example of the fringing electric fields around the secular and around the patch. You can see that this is your L, so this is your W here. Okay, so the field is coming from this. So as you can see that at the center here, the field is very, very low. So this is the example of the magnetic currents for the secular as well as for the rectangular here. Okay, how you want to determine the resonant frequency? So you can use this equation to determine what is the resonant frequency of the secular patch antenna by using this. equation. A is your radius, epsilon r, and zeta here is actually your chi here. We pronounce this one as a chi here. Chi is actually is a constant value due to the modes, right? So what we can see that here for the dominant modes 110, so you can find this is your velocity. So the chi for the dominant modes. For the secular, as you know, that is a TM11 here. So it's roughly about 1.8412 values. Epsilon R is the effective. AE is the effective due to the value of the fringing fields. And V naught is your free space velocity here. Okay, so you can use this equation to determine what is the resonant frequency that can be used. Okay, so how you want to design? Okay, you can use using these equations here, and then you can see that this is a different modes. Okay, but usually we use the dominant modes here. The chi value is equal to 1.841, and you can find the design equation from here for fundamental TM11 mode. So this is the equations that you use. All right, so how you want to use to find out in terms of this secular? Of course, first of all, you need to know what is your epsilon r, your thickness, your resonant frequency, and then of course you need to determine the radius A of the patch. If you know what is the operating frequency that you are looking. Okay, so and then F is given by this particular value. Okay, I think it's not really difficult. The most important things that you know what is the equations that is being going to use for this particular secular patch type of antenna. Okay, so this is the example, the same thing. Okay, the same thing, you need to find out what is the resonant frequency. If resonance is given, and you need to find what is the A here. The radius will determine the resonant frequency of your antenna itself. Okay, so of course, you find the value of your constant F, capital F here. Capital F is coming from this one. As you can see, 8.791 times 10.9 FR. And then you got this value, and then you put into this equation. So you have this particular values of A here. So the A here is getting 0.525 centimeter, where your A effective is getting the value of 1. You have A here, so you can find the A effective here as well. So you can find from this A effective throughout this particular equations. Okay, so this is my pattern, the E plane and H plane for the secular microsтрip. As you can see that the pattern is almost similar. Okay, for your radiation pattern for the secular patch type of antenna, roughly about 90, roughly more similar, 80 to 90. And then as you can see that this is the conductor secular patch, we want to find what is the efficiency here from this directivity. The directivity is given as this, and then you find out your K naught AE over 120, and then you find in terms of the Bessel functions of your resonance input resistance from here, and then you can find the quality factors to determine the bandwidth later on, because this is important in your microstrip antenna. So you need to find what is the quality factors so that you can determine the bandwidth of your antenna. Okay, so this is just a graph, radius and conductors, effective radius, and then you have directivity, and then from here you have efficiency and percent bandwidth, as well as you have the input impedance here. Okay, right. Before we dismiss our class today, I just want you to do this particular cellular telephone satellite. Okay, can you do this example? And then after that, whether the values that you are getting is almost same or not with the value that I'm giving it to you now. And then after that, you can, we can dismiss our class because I have a meeting now. Okay, so can you do it? And then after that, I will give you the what we call the link to have your slide attendance today. Okay, try to. Okay, so next I just want to show you. Okay, so once you got already the answer, so this one is actually I just want to show in terms of how you want to have if you have more than one element. If you have more than one element, so you can have in terms of the series feed and parallel feed lah. I mean how you want to connect the antenna from one to another. So in terms of the array elements, how you want to connect this, we can find out later. Okay, in terms of this. And the most important thing in the corporate feeds, we are talking about the corporate feed here, is the matching. Usually you match with the 50 ohms, and then from these 50 ohms, okay, so you want to find what is the values of this particular impedance lah, right? So for example, so you are using into all the matching transformer, quarter wave, all this. So to match with the antenna that you have, in order for you to make it in terms of the array. Okay, so this is an example of the array. As you can see that this is a time 10 multiplied by 10. So it means that what you can see that the number of elements here is roughly about 10 element and the 10. So this is what we call the planar type of antenna array. So you can see, and then the operating frequency is 2 to 2.3, and this is for the space communication. You can see this is the example of the microstrip array. Okay, so this one you can have it, okay, or you can look and then do it at home. This example here. Okay, right. So I just want to have so this particular extra notes that I'm giving to you. Actually, I got it from somebody else and from the internet as well. So I just want to briefly explain to you the extra here. Okay, I need to share this with my computer. Okay, I change it now, as you can see. Can you see that? Still you are. Can you see? Or you see my previous one?
Yeah, can see.
Can you see? So this is just an extra notes. I think that one is a bit more easier to. Okay, so it's the same thing. The only things that I show you about this microstrip antenna. Okay, so this is the geometry of rectangular, as I mentioned to you before. We have the W, we have the L, we have the height. Okay, the thickness. Note what we can see. L is the resonant dimension. W is really chosen to be. You can see that here I say that W is usually chosen to be less large than L to get higher bandwidth. And so this is why you can see, you can find out that the value of the W is usually greater than L. However, usually W should be less than 2L and W is roughly about 1.5. L is typical. Okay, so I mean, if you want to find what is the suitable patch antenna that you want to design, once you know the W, so you can find what is the L as well. Okay, so this is in terms of a coaxial feed where we feed the antenna here, X naught, Y naught here, and then this is in terms of the resonant frequency throughout the cavity, okay, in terms of L here. Okay, so the same thing, as you can see that we have the same resonant frequency as we discussed before. And then we can see that the resonance is equal to, this is where they use in terms of the cavity of the waveguide models. In this case, M is the modes number, N is the modes number as well, Mn. L is the length of your W, and L is the length of the resonance, W is the width of this particular patch antenna. Okay, So if you talk about 10, the dominant modes here, so you can find this particular F10. Okay, so this is the same values that you obtained as before using this particular called the transmission line method before. So the same thing, you can see that we have the L effective is the L plus 2 delta L. For the dominant modes, we know that C over 2 epsilon R multiplied by 1 over L effective here. Okay, banyak ni baru join mana baru bangun tidur. And then epsilon effective here. Okay, so this you need to find out the value of your epsilon effective here. Okay, because of what? Because of the substrate, different substrate epsilon R and well as epsilon R. Okay, so resonant frequency delta S is usually okay. A good rule of thumb, usually delta L. If you feel that you don't want to calculate, you can find the rule of thumb here using 0.5 H. So you need to know what is the H. From this H, you can calculate the value of your delta L. Sometimes also we need to use the rule of thumbs to find out this particular value. So this is very important as well as your to design. Okay, so this is what you call the resonant frequency here. Okay, so we have the normalized frequency and we have H over lambda naught. So the thickness over your lambda naught is the operating frequency. The resonant frequency has been normalized by the zero order value, where Fn is to F over F naught, epsilon R is to 2.2, W over L is to 1.5. So the basic properties of microstrip, bandwidth, substrate effects. Okay, so I show you bandwidth is proportional to substrate thickness. However, if H is greater than this, but the probe in that become large enough so that matching is difficult. The bandwidth is inversely proportional to epsilon R of foam substrate gives a high bandwidth. Okay, the bandwidth is directly proportional to the width W. Normally W is less than. So this is all the rule of thumbs that sometimes you need to know for the basic properties of these microstrips. Typical result for a typical substrate thickness. As you can see, a typical substrate permittivity 2.2. The bandwidth is about 3% by using a thick foam substrate bandwidth of about this. By using spatial feeding, okay, especially aperture coupling and step, the bandwidth over 50% can be achieved in this case. Okay, so this is the graph bandwidth versus H over L lambda naught here with some epsilon R and as well as epsilon R value 2.2 and 10.8. Okay, so this is input resistance here, how you want to find here. So what you can see, so the rule of thumb as well, if you want to find what is the resonant input, patch is usually fed along the center line, W. Okay, Y is equal to W over 2, the center, to maintain symmetry and thus minimize excitation of undesirable modes. So usually the rule of thumb as well, if you want to find the fit, so you can have half of W with 1/3 of your L. Sometimes you can use that rule of thumb as well. So if you want to find your R in, it's proportional to cos squared pi x naught L. So what you can see that, so you can find your x naught here, the positions that the value of this particular is matched towards your whatever input impedance that you want. Okay, so you can see that the same thing, resonance input RH cos squared pi x naught over L here. So RH usually, if you calculate this value RH here, H is about 100 to 200 ohms. Okay, so this is about your W over L is 1.5, X naught to L over 4, Y naught is to W over 2. So you can find the value of your resonance input resistance here. Okay, so this is the efficiency, of course, radiated over your total. Radiation efficiency is less due to the conductor loss, dielectric loss, as well as the surface wave power. So this is the radiation efficiency, surface wave caused by pattern here. Okay, so your radiated over your radiated plus your another total input power. So this is the in terms of the efficiency. Okay, so what we have here, radiation efficiency in terms of R here, so you can find your delta here, tangent delta conductor loss increases with the frequency, and conductor delta is more important for thinner substrates, and conductor loss increases with the frequency. proportional to square root of your F due to skin effect. Conductor loss is usually more important than the dielectric loss here. Okay, so this is the radiation efficiency for a full substrate. Higher radiation efficiency is obtained by making substrate thicker. For a typical substrate such as this value, the radiation efficiency maximum for H over lambda naught roughly equal to 0.02. So this is all the graph given from the experimentals. You can see accounting for losses, okay, property of microscopic radiation patterns of this E-plane, how it looks like, almost the same as we discussed before. Okay, so directivity, okay, they put in terms of the directivity versus H over lambda naught. And then the model, so this is in terms of the probe model. And then this is how they calculate the values of your Q factor and as well as R in maximum here. Okay, so this is the input resistance versus frequency, input reactance versus frequency, approximate CAD values. Okay, so this is more on the values of reactance here. Okay, so this is what your radiation efficiency calculations. Okay, so this is all actually the extra notes. I can upload it later on your, so that you can have a look in terms of this. From here, if you want to do the analysis based on your simulations, you can try to find out in terms of this simulations based on this particular results that we have here. So these are some of the radiation patterns. Okay, in terms of the mathematical radiation pattern, and also how, in this case, how we want to have in terms of the different polarization. Before this, we are talking about the linear polarization, how we want to change from the linear to secular. So we have three main techniques: single feed, dual feed, or synchronous subarray technique. So this is an example of how you can change the polarization of the patch antenna itself. For this one is a single feed. You can feed at the edge here of your rectangular or secular patch here. Okay, so secular polarization single feed here. How you calculate this X naught and Y naught. Okay, so or you can do some slotted here, or you can use the taper here. Okay, truncated corners, or you can use in terms of dual feed here, okay, with the 90 degrees here, so that you can have do a secular polarization, or you can put the hybrid coupler here, where the hybrid coupler consists of 0 and 90 degree phase here, so you can have, or you can use synchronous rotation, okay, for this particular. So what you can see that you have a lot of different techniques in order for you to use for the secular polarization. So this is a secular patch, as I mentioned to you just now, how to calculate this particular value, okay, for this particular patch here. Okay, so all this one, what you get, and then I did as well for the feeding techniques, and then how you want to improve the bandwidth using probe compensation, improve bandwidth using the strip slope form inverted stack patch. Okay, improve stack patch as well, parasitic patches, direct couple patches, or you can use the U-shaped slot here. Okay, so there is a lot of techniques as well how to improve this particular bandwidth, because we know that the bandwidth of this antenna usually is very small, so that you can improve the bandwidth by using all these techniques. Okay, so these are all multi-band antenna and miniaturization. So this is just the extra notes I gave it to you so that you can have a look, or you want to find in terms of this. All right, so that's all for, I think I need to delete some of this. Okay.